Hello everyone, so this will be a short video on standard voltages and voltaic cells. So before we go to solving problems regarding standard voltages, let's have some definitions. So what are voltaic cells? So in spontaneous oxidation reduction or our redox reactions, electrons are actually transferred, and when this happens, energy is released. We can use this energy to do work if we make the electrons flow through an external device. So we call such a setup as a voltaic cell, or sometimes it's called the galvanic cell. So on your right will be a simple experiment in creating a galvanic or voltaic cells in our laboratory. So you have electrodes, you have wires, and of course we have our voltmeter to measure the potential difference across the electrodes. So let's just go through it. So if we look at it in detail, this is how it looks like. So oxidation actually occurs at the anode. So here you go. And reduction occurs at the cathode. Okay. In this setup, we have zinc, which is on the anode side, and we have copper on the cathode side. So each of the two compartments of a voltaic cell is actually called a half cell. So this is our half cell, and this is our other half cell. So when looking at it, the movement of cations will be from left to right, and the movement of anions will be from right to left. In detail, let's just see the importance of the anode and the cathode. So anode is where oxidation occurs. This is where electrons are produced. It is what anions migrate toward, and it actually has a negative sign. And the cathode, on the other hand, is where reduction occurs. It is where electrons are consumed. It is what cations migrate toward, and it has a positive sign. So if we look at it, let's just zoom that a little. So this is the basic setup. These are your electrodes, and this is our anode side, our cathode side. This is usually negative, and this is positive. So our electron flow usually is from this to that side, and of course, it follows on the cathode side. That is how it moves. And in between our two electrodes will be a salt bridge to facilitate the movement of the chemicals. And actually, the difference is what you call your potential difference. So this is just a very simple um, illustration on how a voltaic cell works. So, of course, it's not always just a figure or an illustration. We're more on our target for this module is actually to solve voltaic cells. So we need to understand the cell diagram notation. The reaction in a voltaic cell may be represented using a cell diagram or a cell diagram notation, where you place the anode on the left and the cathode on the right. A single vertical line represents the boundary between two phases, and the double vertical line actually represents the salt bridge. If we just zoom them, we can see. So let's just highlight our cell notation. So that is actually our cell notation. Zinc, the zinc pair is the anode pair, and the copper will be our cathode pair. So you can see the single, let's just remove the highlight. This is our single vertical, I'm sorry. This is our single vertical line. And we can also see this is our single vertical line, which talks about phase boundary. And we have the double vertical line, which is actually the salt bridge. And of course, just to highlight it more, it says here the single vertical lines indicate the species that are in different phases. In this example, solid and aqueous. And the double vertical line indicates the half reactions are in different cells as separated by the salt bridge. So in block diagram, so our anode will always be on the left side, our cathode will be on the right side, and in between will be a salt bridge. And of course, moving to what we need, we'll be doing the standard cell potential computations. So the cell voltage of voltaic cells operated at 25 degrees Celsius under standard conditions is referred to as the cell potential or standard voltage E. The standard cell potential is the potential difference between the cathode and the anode. So it's always the reduction side minus the oxidation side, or the voltage across the cathode minus the voltage across the anode. Remember, again, these are the pair: oxidation, anode, reduction, cathode. Always remember that. Just make sure that that is clear and you always remember that. And I'm sure that for every problem regarding standard cell potential, you can get it. Always remember the pairing. And of course, to help us in getting the cell potential, it's called the potential difference because we will be comparing the voltages of reactions, and their difference is actually what we call our voltage. So we have a given standard reduction potential at 25 degrees Celsius table, and in this table, always use this table when it's at standard condition. There's another table for reactions not at standard conditions, and you know that the standard condition will be 25 degrees Celsius. So we'll be referring to this table every now and then when solving our problems regarding standard cell potential. So this will be a very, very helpful table, and you can see that in the table, the strong reducing agents are at the bottom and the weak reducing agents are at the top. Likewise, the weak oxidizing agents are at the bottom and the strong oxidizing agents will be at the top. And remember, this table talks about reduction potentials. So where is the reduction potential? So usually reduction, it's always we're actually referring to the cathode side. That's why stronger oxidizing agents are at the top and stronger reducing agents are at the bottom. Okay. Because a reducing agent is in charge of oxidation and the oxidizing agent is in charge of the reduction. So let's go to problem solving. And before we go to that, let's try to get the steps on determining the cell potential as how we were always doing in redox reaction. So first, write the oxidation and reduction half reactions for the cell. Second will be look up the reduction potential of the half reaction in the table of reduction potentials. Refer to the table that we had on the last slide. The more positive the reduction voltage, the greater the tendency is for the substance to be reduced and therefore the better oxidizing agent. The half cell reactions are reversible. If you need to reverse, you must change the sign of E. And then add the potentials of the half cells to get the overall standard cell potential. And the calculated cell voltage is always a positive quantity for a reaction taking place in a voltaic cell. But remember, when using this, you first get the value of the voltage as it is and then apply the formula. Again, even if the reaction was reversed, for example, Fe plus 2E yields Fe, and in our half reaction, we are using Fe yields Fe plus 2E, you would still be using 0.45, negative 0.45. Again, do not reverse the sign of the E at the onset. If you need to reverse it in the formula later on, but when you get the voltage from the table, you use them as they are. Okay. I guess to better understand that, let's go through a few problems. And lastly pala, just to remind you, in determining cell potential, when selecting two half cell reactions, the more negative value will form the oxidation half cell or the anode. So the more negative, that is the anode. And for example, consider the reaction between zinc and silver. So let's go to the standard cell potential table. So this is silver and silver. Let's validate that. Let's look for silver. So this is silver, and that's zero point 0.8. And the other reaction is zinc. Let's validate that if that's 0.76, negative 0.76. Here we go. So those are valid values for that slide. So this is zero point 0.8 and 0.76. Since this is more negative, then that will be your oxidation half cell, or that will be your anode part. Okay, so if you need to do the cell notation, we said that anode will be on the left. So we can say that this is, just to get the cell notation, that's Zn2 positive, Zn, and then salt bridge, Ag, positive, Ag. So that's how you do it. This is now your anode side, and this is your cathode side. And let's start with the first example. A voltaic cell is comprised of permanganate and manganese and zinc cell. Calculate the standard cell potential difference delta E. So basically, you're not asked of a cell notation. You're only asked to get the cell potential difference. So what do you do? Of course, we first identify the half cells. So let's first use the permanganate. So that's MnO4 negative yields manganese 2 positive. You have to carry the charges as well. And the other pair is zinc 2 positive and zinc. Now, our, our rule a rule that we will never forget when it comes to chemical reactions is you have to always work with balance equations. So of course, what was our rule before? This is still part of redox. So first, we have to balance non-oxygen and non-hydrogen. So manganese, one of each, that's good. The second one, zinc, that's good, one of each. Next, balance oxygen. But since we're missing oxygen on the manganese side, so we have to add water. And since that's 4, we add 4 molecules of water. On the zinc side, we don't do anything. However, because of the occurrences of water, 4 molecules of water, there's a need to add H positive ions. We have 8. There you go. And on the zinc side, no change because there's no presence of neither oxygen nor hydrogen. So next will be to balance charges. So in balancing charges, we check if both sides are balanced. So on the permanganate side, we have positive 8 minus 1, so that's positive 7. On the right side, we have positive 2. So to balance that out, let's put 5 electrons. And on the second equation, we have zinc. On our zinc side, we have to add, there we go. So we're almost done. We just have to identify the voltages. So the first one will be the permanganate side. We go back. I'm really sorry, I was not able to put the table on another tab. So just have to go back and forth. So let's look for permanganate. There you go. Found it. Our permanganate side is, there you go, it's 1.51. And the other one will be, let's just put that first. So this is equal to 1.51. And for the zinc side, let's look for zinc. Here we go. We already highlighted it a while ago. That's negative 0.76. And as we've said, the more negative will be our oxidation side. So this is where oxidation occurs, and this will be our reduction side. And we're almost done. So to finally get the cell potential difference, so delta E, that will be equal to the E of the reduction side minus the E of the oxidation side. Then all you have to do is get it from the values we've obtained from the table. That's 1.51 minus negative 0.76. So this is equal to 2.27 volts. That's how easy it is to get the standard cell potential. But to be able to do that, you have to, of course, work with balance equations. You follow our rules for redox, and then go to your standard reduction potential table, get the correct values, and of course, finally just use the formula that we already presented, which is it's always reduction side, the standard potential at the reduction side minus the standard potential at the oxidation side. So that will be 2.27 for this. So this is our answer for this example. Okay, probably can have another one. So, by the way, for this example, you were asked to get the half reactions. What if the half reactions were given? Then you'll have it easier. So all you have to do is go to your standard reduction potential table and get the values. This will be for cadmium and tin. So let's look for cadmium. So that's CD. So you have to be careful in using the table. This is CD. Again, just write whatever you see. So that's negative 0.4. And the other one is SN or tin. We look for SN. Here you go. So SN is 0.15. So let's remember that. That's 0.40 and 0.15. So let's put those. That's 0.40. So this is 0.40 and then 0.15. Let's verify that again. That's okay. It's negative 0.40. You have to see what I was telling you. You have to make sure that you get the correct values. Again, the more negative it is, that will be our anode side, like in this case. So the negative will be the one on the oxidation side, and this is our reduction side. So what do we do next? So all you have to do now is, of course, after identifying the cathode and the anode, we use our formula. So that will be equal to, going back, E red minus E oxy. Sorry. So our reduction side is equal to 0.15 minus negative 0.40. So this is equal now to, let me just check that again. Yes, it is 0.15. So that is equal to 0.55 volts. Okay, that's our answer for this problem.